always been fascinated by robotics, and always wondered, what it would take to connect one to a computer and play with it. And I guess I did talk enough about it that my good friend from Germany, Jens Eike, last year at the Chicago International TI Fair, gave me a robotic arm, which is shown here, and told me to stop talking and actually do something about it. So I decided to do exactly that. So what is this robotic arm exactly? In Europe, it's marketed and sold by Playtastic, but in the United States, it's sold by OWI Robotics as a kit. And I actually bought an additional arm from the United States for about $30 from OWI Robotics. It's the exact same arm as the one Jens gave me, except rebranded. This arm comes as a kit, as has been stated, with various parts, gears, and manual controller, etc. I should mention that this arm is a very, very basic arm, which means it's only got regular motors, small motors, fairly low quality, no sensors, and no electronics whatsoever. It's essentially motors and gears, and designed to be controlled with a manual controller. And this is the one that you built from the kit. And it connects via a cable to the robot arm in the back right here. And that's fine and dandy. It's really fun to play with, to be honest with you, as robot arms are concerned, and you can't really beat the price at $30. However, I really wanted to not just have it as a remote control toy, but also be able to program it via a computer. So my favorite computer is, of course, the TI-99 4A, which I first got back in 1981 and have been programming it since then. So how do I connect this to this? Well, it's interesting. My background has nothing to do with electronics or computers, by the way. Actually, I couldn't be any further removed from that. So I did some little bit of research, not a lot, but enough to allow me to first design an interface shown here, and create a custom PCB out of this. The design of the PCB is pretty straightforward. So the first decision was, how do I connect the arm to the computer? And since this arm in particular has 5 motors, obviously using a serial line would not be enough. I needed more control lines. So the next obvious choice on the TI-99 4A was to use the parallel port on the RS-232 card. And so on a classic system for the TI, the card is actually enclosed in the peripheral expansion box, which you can see under my desk here, and it has a serial connector and a parallel port connector. This is what the RS-232 card would look like, and it has a bus connector on the bottom to plug into the peripheral expansion box, something we're pretty familiar with modern PCs, and it's got a serial connector here, RS-232 serial connector, and it also has a parallel port right there, which I used to connect the robot arm to the computer. So now that the decision I was made to use the parallel port, I used a classic printer cable, which is available for the TI, and used the Centronics end to split the cable and basically create individual lines for each input-output port on the parallel cable. The parallel port on the TI has typically 8 input-output lines. These are the classic ones. But it also has an additional 3 lines, which can also be used for any purpose you want. The parallel port on the TI is very easy to program, which was an added factor for me to use it. So clearly one cannot connect this straight out to this without some kind of interfacing electronics. So what I did is I used what we call double pole, double throw relays, some Darlington power transistors and some low power switching transistors to create an interface. And the way this works is very simple. The function of the relays is to simply reverse the polarity of the voltage to each motor from M1 to M5, and the reversing is controlled by these switching transistors, which are connected all to a single port on the parallel connector. Now I could have essentially used one port for each of these transistors, but I really wanted to preserve some free ports for future use. The power to each motor is controlled by these power transistors, which are Darlington transistors, essentially consisting of 2 or more transistors connected in serial to be able to handle higher current. And again, these are all connected each individually to a single port. And finally, I used a single switching transistor here to a single line on the parallel port to connect to the LED, which is found on the nose of the robot arm. So essentially I use software to control the turning on and off of the motors via these transistors, and other software commands to reverse the polarity so that the motors run in forward and reverse. And finally, commands to turn the light on and off. Really not terribly complicated at all. This is, like I said, a home designed PCB. Obviously you can do a bit better with a commercial PCB house, but there's a little bit of macho about doing your own PCB. I don't know. It just feels that way anyway for me. So why don't we go ahead and connect this robotic arm. But first, let me show you what exactly is this arm. The arm consists of a base. Let me see if we can get some better light on this. So this is the base, and it rotates left and right. Then there is the shoulder right here, which moves forward and backward. This is the elbow, which again moves up and down. This is the wrist here, again up and down. And this is the clamp. I'm sorry, I think I missed something. This is the shoulder, this is the arm, okay, this is the elbow, this is the wrist, and these are all moving up and down. And finally there's a clamp right here which goes and opens. And there is a light right here. It's an LED which turns on and off. Like I said before, all these motors, all these functions are controlled by really small motors and a bunch of gears. And it has a surprising amount of torque. However, these are not really high precision motors, and certainly not servos, and therefore there's definitely variability in how they run, and there's also some inertia in that. By that I mean the motion doesn't stop immediately, and so you can get residual motion when you start and stop a motor, and all this adds up to some inaccuracy in the movement of the motor, particularly when you are programming it. So what I did is I basically extended all the wires that come from each motor, and created single pin connectors that will go on these pins here for each motor, for the LED right here, and for the power connector. So now I have my TI-99 4A system on, circa 1981, and I'm gonna go ahead and start a program called the Robotic Arm Controller program, which I wrote in assembly. And this program resides on the SK5, which is my IDE drive. And basically it controls all the functions of the robot arm. There are two modes of operation. There is a manual mode and a program mode. In manual mode, if I press M, basically I can select the motor that I want. Motor 1 being the rotating base of the arm, and then moving upward to motor 5, which is a clamp. So I can go to any motor I want. And then I use the arrow keys. So I select the motor and then use the arrow keys for this motor, it's left and right, to control the arm. And so on and so forth. I can press also L to turn the light on or off. Press Control M to go back to the main menu, and then in the program menu I have the options of recording a new program, replaying a stored program in memory, load a program from disk, and save a program to disk. And so the way I implemented the programming is, instead of just using a scripting language or something of the kind, given how inaccurate that robotic arm is, the easiest way to program it was basically to move the arm the way you want it manually and have the computer record every movement you make and then store it in memory, at which point you can choose to save it to disk, or if you're not happy with the results, record a new program. And you can replay the program that is stored right away, you can check your results. Motor control is primarily achieved by simply recording only the number of the motor or of the light being used, and then the motor is moved a very specific fixed amount of time. Therefore, every press of the keys moves the motor in a small amount of time, for a small amount of time, and then it's replayed the same way with some variation in the timing. The manual control it uses a very crude version of what we call pulse width modulation, which essentially turns on and off the motors at high speed in order to control their speed a little bit. This makes the manual control of the arm a bit easier and more precise. However, playback is done at full speed. So I use a variety of counter loops and delays in order to match the replay speed to the manual speed with pretty much fairly good results. It's not 100% accurate, but it does work for the most part. So I'm going to go ahead and demonstrate the manual control first. So I'll go back to that. So manual control. Then let's say we select motor 1, which is the base, and I can move it left and right based on my motion. Then select motor 2, and let's say we want to bring it down, bring it up. Motor 3, again, up, down. Motor 4, same thing, up, down. And finally the clamp, which is motor 5, and that's open, which is already open, and closed. And let me just actually get motor 4 out so you can see better. And motor 1, and then I can turn on the light. There you go, on and off. So pretty cool. But of course I didn't want this to be just a glorified remote control. So let's go back to the main menu and programming mode. So now I'm gonna just demonstrate how to record a program, just a simple one. And so let's press R for record. So it says recording in progress. Nothing happens until you actually move the robot, and it only records the steps that you do. So let's go ahead and do something. Let's say rotate the arm. Select motor 1. Let's rotate the arm this way. Actually, you know what? Let me just stop that for a second. I forgot to mention that because this arm has no sensors whatsoever, there is really no initialized state that you can detect for this arm. So I have to start it every time from an initialized state whenever I want a program to run. Otherwise, the starting position is unknown to the program, and this could get you into all sorts of trouble. So why don't we go back into manual mode, and let me just set the arm into its initialized state, which is basically a centered arm with everything down. Okay, and the clamp fully open. Alright, so that's the initialized state. From there I can go back to programming mode, and now I can record a new program. So let's go ahead and bring this down a little bit. That's moving forward, and why don't we just rotate it? Turn the light on. There we go. And let's get the arm down a bit further. Okay. That's enough for a demonstration. So now I press Control E to end. So now I have a program stored in memory. So I can replay it. But of course I can't replay it from that position. I have to go back to the initialized state. So time to go back to manual and again reset the arm. So it's kind of a pain, and that's one of the major limitations of something as primitive as this arm, in that you don't have this initialized state. I am dabbling with the idea of actually putting switches, micro switches, at some point in there, which I can connect to one of the empty ports to indicate whenever a motor is running, bumping against its end of travel. And that will allow me to actually automatically create an initialized state for this arm. So let me bring it back to initialized state. That's already there. Okay, so we're back on initialize fade, so let's go back to the main menu, program, and so on. I'm going to replay now what we have just recorded. So just press P, and notice how the speed is going to be faster because this is running at full speed now, without pulse width modulation. There we go. So you notice it did touch a little bit on the table, so there is definitely some inaccuracy because of inertia. It's hard to control that inertia very well, and I have been playing with different counters and delay loops to try to counteract that. It's not fully precise, but it does work, as I will demonstrate shortly. So that's for the recording. So next I'm going to show you a stored program which I already recorded previously. So I have reset the position of the arm to its initialized position, and I'm going to run a program which essentially rotates the arm, picks up the little Sharpie here, and puts it around there. So let's see how that goes. There are no guarantees that it always works, because there is slight variability every time, but usually I'm able to get it to do what it's supposed to do without too much difficulty. So I've already saved the program, so let me go ahead and load it here. So it'll take a few seconds to load. Here we go, and now we're gonna press P to play. And here goes nothing. And there you go. So this is a successful run. So as you can see, it does work. It's not to be used for accurate work such as drilling a hole in a tooth at your dentist's office, but for relatively coarse maneuvers, this works pretty well. Well, I don't know about you, but I think this is cause for celebration. Cheers!
Talk to the OWI-535